Okay, in the next couple of sections, and we're going to take a couple of videos to get through this section 5.4, we're going to talk about why we learn to integrate functions. And there are several applications for why I might want to integrate, and I'm going to introduce one particular application to talk about finding areas underneath a curve. So you know how to find the area of a lot of different geometric figures. We have formulas for, say, a rectangle. We can find the area of a rectangle by doing length times width. Or if I have a triangle, I can find the area of that triangle by doing 1/2 the base times the height. But what happens if I want to find the area of something that doesn't fit one of those standard geometric figures? So let's take a look at this picture here. I have drawn a part of the curve, 1 minus x squared, but I've chopped it off so that we're only looking at the interval between 0 and 1. So what happens if I want to find this area underneath this curve? So when you look at that area, notice it does not fit any particular geometric shape because of that curved edge that function 1 minus x squared creates. So what if I want to find the area for that? Well, this is where integration is going to come in. And I want to talk through just real quickly a little bit of how I am approximating that area using integration. So what we're going to do is we're going to start off by splitting this area up into rectangles because we do know how to find the area of a rectangle. So I'm going to draw in some rectangles here, and what I'm going to do is I'm going to start at my leftmost part of my interval at x equal to 0 and create the left corner of my first rectangle. And then I'm just going to draw in my rectangle. I'm going to pick a particular width and sketch in a rectangle. Use a different color here. And then I'm going to choose my next rectangle. I'm going to pick, again, a leftmost spot of my rectangle to be on the curve, and then I'm going to draw my next rectangle. And I'm going to continue to do that until I cover that whole region. So when I do that, it's going to look like this. These are a little wider than the ones I was drawing, but you're going to pick a particular width for your rectangle that remains the same. So here, dividing it up into 4 pieces, so if I split my interval from 0 to 1 into 4 pieces, each of the widths of these rectangles is 1/4 unit wide. So you want your rectangles to be the same width for each one. Now, of course, the heights are going to differ. And the way these ones were created, again, was to put the leftmost corner of that rectangle on the curve and then draw the rectangle based on that width that you've decided to make your rectangles, which in this case was 1/4. Now, these ones are called left rectangles because I'm using the leftmost corner of the rectangle to touch the curve. You can use a rectangle where you use the right corner. So if I use for this first rectangle the right corner, then the rectangle would look like this, and my rightmost corner here. So you can use the right corners of the rectangles to draw in your rectangles over that area. It doesn't matter which one. If you notice, there's going to be some issues with either rectangle that you draw. For example, with the leftmost rectangles, notice that I'm picking up area in these rectangles that I don't want. I'm picking up area that's not included in the area that I'm trying to approximate underneath that curve. So my estimation is going to be too big. Whereas if I use the rightmost corner of the rectangle, what I'm doing is I'm going to create an area under here that's not going to be enough, and I'm going to actually lose some area that I want, so my estimate would be too low. So there's issues regardless of whether you use left rectangles or right rectangles. So for the purposes of this discussion, we're just going to stick with left rectangles. So we know that the area of a rectangle is length times width. So what I'm going to do now is compute the area for each one of those rectangles and add them together, and that will be my approximate area under the curve. And then we'll talk about how you can get a better approximation. So first of all, I already mentioned that the width of each one of my rectangles is the same. Oops, not 1/2, it's 1/4. So each one of these rectangles has a width of 1/4. Now, the length of my rectangles is the height of this rectangle. So the way that I'm going to find the height of each rectangle is I'm going to plug in my x value of that leftmost corner. So if I plug 0 into the function, that's going to give me the height of this first rectangle. And if I do the next leftmost corner and plug in f of 1/4, that will give me the height of the next rectangle. And the leftmost of that would be plugging in 1/2, would give me that third height, and my fourth height would come from plugging in f of 3/4. So I know a value, for example, if we take this first leftmost corner, if I plug in 0, I get 1. So I know that the area of this first rectangle is 1/4 times 1. And then I'm going to do that for each one of those rectangles. So I've shown that here. So in red there, we have the y value of plugging in each one of those. So that's the height of my rectangle. And then, of course, the width of each rectangle is the same. They're both 1/4. So if I do all of that arithmetic, here is my approximation. We have an approximate area of 25/32 units. Now, I mentioned before that when we're looking at this, I'm picking up an awful lot of area that I don't want. So in that calculation, I'm including this part, and this part of those rectangles that really aren't under the curve where I'm trying to approximate my area. So I want to try to do this same process, but I want to make the rectangles smaller. Because the smaller that I make my rectangles, the better my approximation is going to be. So that was 4 rectangles. So let's see what happens if we increase the number of rectangles that are drawn underneath that curve. So when we're looking at this next one here, we've got 8 rectangles being drawn. So we doubled it, and then doubled that again to 16. And then this last one took it all the way up to 128 rectangles. So notice that with each increase of the number of rectangles, that extra area that I don't want gets smaller and smaller and smaller. In fact, in this last drawing, you can't even see any of that extra area in the drawing. Okay, so now imagine what would happen if we let the number of rectangles approach infinity. So if we have the number of rectangles approaching infinity, anytime I have a variable approaching a value or approaching an infinity, you should be thinking about limits comes to mind, and that's exactly what we're going to do. So to compute the area, what we're going to do is allow the number of rectangles to approach infinity. And so, excuse me, the R and the L are just those different types of rectangles that I was talking about. Either a leftmost rectangle where you're using the left corner of the rectangle, and this is using the right corner of the rectangle. So based on what we were doing, we would be using this, letting the number of rectangles approach infinity, And then this is the summation symbol. So all it says is that you're going to take and compute the area of each rectangle. There's the y, there's the x, so there's the height and the width of my rectangles. And you're going to do that for each one of your rectangles from 1 to infinity, and you're going to add those together. That's what that summation symbol means, is that you're doing each one of those areas, adding them together, and then that's going to be what your overall area is. So obviously we can't add up an infinite number of areas, so that's where our integration is going to come in. So instead of doing this specifically from 1 to infinity, and we can use this if we determine that we're going to use a finite number of rectangles. For example, if I use the 128 rectangles, then I could use this formula where n would go from 1 to 128. But if we want it to approach infinity, we're going to define this to be a definite integral. Now you've had integration already. You've been working with the properties of integrals to do some indefinite integration. Now the integration that you've done in the past was indefinite integration because if you looked at the notation, there was nothing here on your integral symbol. You just had the integral symbol. Now what we're going to do for a definite integral is add two values here and here, which are called the limits of integration. And what they're going to define is that interval where we're kind of cutting off the function. So if you look back at the area that we were calculating back when we only had 4 rectangles here, if I were going to write this out as an definite integral, the way that it would look would be this. I would have my integration symbol, and then my limits of integration would be the interval for which I was chopping that function off, for that area that I was looking at. So my limits of integration would go from 0 to 1. And then what I'm taking the integral of, my integrand, would be the function that created that curve, which was 1 minus x squared, and then that dx notation, which just says with respect to x. So one other thing about limits of integration, typically when you write your limits of integration, this number here on the bottom will always be the smaller value, where the limit on top will always be the larger value. Okay, so there are a few properties of definite integrals that we're going to look at in some examples where we're specifically talking about area and talking about these properties. And then in the next video, we'll actually do some evaluation of these integrals using the fundamental theorem of calculus. For now, I just want you to get used to these properties and to try to wrap your head around what it is we're calculating when we do a definite integration. Okay, so the properties real quick, you can read through these on your own, but the first property says that if my limits of integration are the same, if I go from a to a, I'm not really going anywhere, so that value would be 0. The other thing is, the second property is I can flip those limits of integration if I pull out a negative. We don't usually use this property too often. It might be used if I want to simplify my integrand a bit. But this negative, we don't have to pull the negative out because that negative will show up when I integrate this in my calculation at the end. The third property says that I can pull a coefficient from my terms in my function out in front of the integral, which might make it easier to integrate, or if I know some particular definite integral values already, then this might be helpful. Property 4 states that I can split an integrand at an addition or subtraction sign by writing it as the sum or difference of two different integrals. That allows us to split up all of the terms within a function into separate integrals. And finally, the last one says that if my limits of integration go from A to C, that if I want to cut that somewhere midway between A and C into two separate integrals, I can do that. So notice that if I'm going from A to C, what it basically says is that I can go from A to B, somewhere in between, and then pick right back up at the B and finish at my C. So as long as this sum here covers the overall limits of integration, that interval from A to C, which it does, I start at A and I end at C at the end of that sum, then those integral values are equivalent. Okay, so let's put these properties into practice in a couple of examples. Now, in this first example, you are actually given what the value of some particular integrals are. We know that the integral from 0 to 2 of x is equal to 2. The integral from 0 to 2 of x squared is 8/3. And the integral from 2 to 3 of x squared is equal to 19/3. So what we want to do is evaluate some definite integrals where we may have to use those properties in order to use these values that we were given in the problem. So in this first example, part A, we're asked to find the integral from 0 to 2 of 9x squared minus 4x. But remember, in the original problem, the integrals that I was given from 0 to 2 had integrands of x and x squared. So what I would like to do in part A is split this up so that I get integrands of x or x squared. And the properties allow me to do that. The first thing the property allows me to do is split this integrand at the minus sign and write it as two separate integrals. The integral of 9x squared minus the integral from 0 to 2 of 4x dx. And I lost my dx there, don't do that. So after each integrand, I need that dx with respect to x. That notation is important. Okay, so I've got it split up into two definite integrals from 0 to 2. And again, I specifically want, based on what I was given in the problem, an integrand of x and an integrand of x squared. So now I'm going to apply the property that allows me to pull this coefficient out in front on each one of those, and I'll have then an x and an x squared in my integrand. So I'm going to have the integral from 0 to 2, and I'm going to pull my 9 out front, leave my x squared in my integrand, minus on the next one, my integral from 0 to 2, I'm going to pull that 4 out in front, leave my integrand x, and now what I can do is some quick substitution. So I can substitute the integral from 0 to 2 of x squared dx was given to me in the problem as 8/3. So I'm going to bring down my 9, substitute in my 8/3, and then I'm going to do a similar thing on this second integral. I know that I can substitute the integral from 0 to 2 of x dx was given to me in the problem as 2. So I'm going to bring my 4 down, substitute in my 2, and then just do the arithmetic. So 72/3 minus 8. 72 divided by 3, of course, is 24. Minus 8 gives me an overall value of 16. Okay, so if you want to take a second, see if you can split up part B, and then come back to the video and see if you got your answer right. On this second one, I am given a definite integral from 0 to 3. But when I look back at what I was given in the problem, I don't have any integrals that go from 0 to 3. But what I do have is an integral of x squared that goes from 0 to 2. and an integral of x squared that goes from 2 to 3. So if I combine those two, I would have an integral of x squared that's going from 0 to 3. So what I'm going to do is split this up into the sum of these two integrals. So I'm going to have the integral from 0 to 2 of x squared dx, and I'm going to add that to the integral from 2 to 3 of x squared dx. So it's covering that same interval from 0 to 3, but just in two separate integrals. And now I'm just going to substitute. So we know that the integral from 0 to 2 of x squared was given to us as 8/3. And the integral of x squared from 2 to 3 was given to us in the problem as 19/3. So if I add those together, I get 27/3, which is equal to 9. So you just want to try to split up using those properties so that you can get an equivalent sum, difference, product of integrals that match what you were given in the problem. Okay, one more quick example, and this one's focused primarily on area. So you're given some regions in a curve, and you're given what the value of those areas are. So we know that the area of that area A shaded in yellow, we know the value of that is 3.45. And then we're also given the values of areas B and C. Now, this is going to bring up one other property that we need for calculating area when we're on the XY plane. And that is that any areas that are below the x-axis are going to be considered negative values. And any areas above the x-axis are considered positive values. So when you're doing these calculations, you want to be careful that you carry the right sign with you when you're writing out the areas. So in this first example, we're asked to calculate the integral from a to 0 of that function. So when I'm looking at the picture, the area that lies in the interval from a to 0 would be area A. And because that is below the x-axis, I'm going to indicate that as being negative 3.45. So that negative symbol is indicating a location of that area with respect to that x-axis. Okay, in part B, we're asked to calculate the integral from A to B for that function. So that's going to be all the way from A to B, so it's going to be all three of these areas combined. And just watch your negatives and positives. So we want to add area A, which is negative 3.45, together with area B, which would be a positive value because it's above the x-axis, and add that to area C, which would be negative 1.18 because it's below the x-axis. And so now all I want to do is get on my calculator and do that arithmetic. And if I get on my calculator and do that, I ended up with an overall value of negative 1.87. Okay, so you'll have a few questions like this where you're just applying the properties, but now we want to take a look at how do I calculate an integral of a function, say that integral from 0 to 1 of 1 minus x squared dx. How do I calculate that integral if I don't have any areas to go off of, and I don't want to add up all of my rectangles and do it that way? So the next video will take you through the fundamental theorem of calculus, which will show us how to evaluate definite integrals.